This is very important question of abstract algebra. We have to prove order of conjugacy class of A is equal to order of G by CA. Can we say it is order? Okay. Number of elements CLA this means number of elements is conjugacy class of A is equal to the number of elements in this group G by CA. Okay. So order are same. We have to prove this. First, I will explain what is CL of A and what is G by CA. Okay. Let G be a group. Let G be a group. A be an element in the group G. So we can define CL of A. This is the collection of all elements B, which is can be written as X A X inverse. That means you take X from G and make this group X A X inverse. Collect it the elements X A X inverse. Compute X A X inverse, and the elements will be come to this CL of A. Okay, so such that X belongs to G. And what is G by CA? CA means CA, that means centralizer of A. This is the collection of all elements X belongs to G such that AX is equal to XA. Collection of all elements which commute with A. And what is G by CA? G by CA, sometimes it is written as GCA. Both are same. Okay. So this is equal to, this is the group of all left coset. This is factor group and it is the set of all left coset XCA such that X belongs to G. So these are okay. Now we have to show that order of this number of elements in conjugacy class of A is equal to order of the group, order of the factor group this, order of G by C. Okay, order of the factor group this. So what we have to do? We have to make a bijection from this set to this set. This is a set and this is also a set. If we can make a bijection from this set to this set, then we can say number of elements are, so that we can say this order are equal. Okay, number of elements are same. So first make a function. Okay, try to make a function from this to this or this to this. Okay. After making the function, check is it well defined? Yes, it is well defined. Then check is it 1 1, is it 1 2? Okay. So well defined 1 and onto this 3 we have to check. By first we have to make a function from this group to this group or this group to this. I will make a function from this group to this group. Okay. So let phi is a function phi from G by CA, that means this is the factor group, to CLA. So I am making a function such that, what is the function defined as? Function is defined as like this, such that phi of elements in this is of the form XCA. So यहाँ पे, so elements are XCA. This is the left quotient. Okay? So phi of XCA, this will be equal to elements in this form XA X inverse. So I am just defining a relation. Okay, phi. Now is phi is a function? If phi is well defined, then phi is function. Okay. So now we have to say that this phi is well defined. Okay. Okay, now I am going to check well defined. In this part, I taken help from my professor, Dr. Pankaj Hajalika sir. So the man behind this solving of this problem is my professor, Pankaj Hajalika sir. Okay, so he is helping me. We have to check well defined. So how to check well defined? Take any two elements in this group. Take any two elements in the domain and check it, so that the images are equal. Take any two elements and they are equal. If take any two elements, let's say let x ca and y ca. These two are left person, and these two belongs to the group G by Ca. We are taking two elements in this group in the domain and assume that these two elements are equal. Then we have to show the images are also equal. Then it is well defined. That means same element cannot have different images. Okay, so it will be well defined. So let take that these two are equal. Let these two belongs to this and x ca is equal y ca. Okay. Now AH is equal to BH, where AH and BH are two left person. Then what happens? If and only if A inverse B belongs to H, A inverse B belongs to H. Okay. And what will be here in this case? This will imply X inverse Y belongs to C of A. Here is in the place of H, it will be C of A, centralizer of A. This element belongs to C of A. This means what? X inverse Y into A is equal to A into X inverse Y. This is the definition of C of A. AX is equal to X. So this is okay. Now what happens from this? Multiply by X. Here it is X inverse YA. So left multiplication by X and right multiplication by Y inverse. You will get AX inverse. Okay. AX inverse Y. Okay. So here you are multiplying by X. Also here by multiply X. Here you have right multiplication by Y inverse. Here is some right multiplication by Y inverse. Then you will get Y inverse is equal to, from here we will get X inverse, because when the bracket will be removed, X inverse it will be identity and Y inverse will be here remain, and similarly where this bracket will be removed, Y inverse will come to here, Y inverse will become identity E and it will be remaining X inverse. Okay, so this is the part. So if this, and what is this? This is the, okay, phi of this. What is this? This is equal to phi of XCA. So in place of where it is Y, where it is Y inverse, then it will be phi of YCA. Okay, phi of YC. Phi of YC is equal to phi of XCA. elements are equal and their images are also equal. If the two elements are equal, the images also will be equal. So that means it is well defined, hence well defined, hence well defined. You write hence well defined. Okay, well defined sort. Second part is we have to show. Can I remove it? Note down, I will remove. Secondly we have to show it is 1 1. What is 1 1? It is the reverse process of well defined. Take any two images, take any two element and let the images of the two element are equal. Then you will get, if you will get actually the elements are equal. If images of two elements are equal, you take, then you will, if you get actually the elements are equal, then it is 1 1. Okay, okay, 1 1, that means here take any two elements and images of that two element. If these two elements are equal, these images are equal, then these two elements are also, three images are equal. 1 1, that means what? Two different elements cannot have same images. Different elements have different images. That is 1 1. Two different element cannot have same image. That means if images are equal, then the three images must be equal. Okay. So that is 1 1. So take any two images, take any two elements and their elements images. So what elements we taken? The elements we taken are these XCA and YCA. These two are elements in the domain G by CA. Okay. We have taken. Okay. Now let the images of these two elements are equal. That means you take, let phi of XCA is equal phi of YCA. Phi of YCA. Okay. Images are equal. So we are going to show that XCA is equal to YCA. It will give us that XA X inverse is equal to YA Y inverse. Phi of this means this, phi of Y this means this. Okay. Okay. Now that means we are going to show that these two are equal. When any two causes AH and BH, these two are coset, when it is equal, these coset are equal, AH is equal to BH, if and only if A inverse B belongs to H. We are going to show A inverse B belongs to H. Here we are going to show X inverse Y belongs to X inverse Y belongs to C of A. We have okay, any two cosets AH and BH are equal when A inverse B belongs to H. From here, using this, we are going to show that X inverse Y belongs to this C of A. Okay, subgroup is this CA. Okay, H means CA here. Okay, so X inverse Y. multiply x by x inverse, it will be x inverse x. Here it is x a x inverse, and here it is y a y inverse. Multiply here by, we need x inverse y. Multiply here by x inverse. So let's multiply by x inverse. Then it will be cancelled x inverse. Here multiply by y, and here multiply by y. Then you will get ax inverse y. It will be x inverse y, and y into y inverse, it will be identity A, and identity, that means B. And if we multiply by identity, so nothing to be written. So E means multiplication like 1. Okay. Yes, do you understand this step? Okay. So A into x inverse y is equal to x inverse y into A. That means x inverse y is commute with A. That means x inverse y will belongs to centralizer of A. If x inverse y belongs to centralizer of A, this will imply XCA, according to the property of cosets, I am telling you twice, okay? This will be equal to YC of A. XCA is equal to YC. So, images are equal, that means the pre-image, that means, okay, the two elements are equal. So, it is 1, 1, right? Hence, it is 1, 1. Last thing we have to show onto, okay? Last part we have to show onto. Onto is very simple. Take any element in the codomain. What is codomain? We are defining function from this to this, so codomain is this. So let x, okay, let z a z inverse, z a z inverse. This is an element, okay. Z a z inverse, this is one element, because z a z inverse, these three elements are from Z. So by closure property, it will be, after computing this, it will be only one element. Suppose let's say it is B. Okay. So Z a Z inverse belongs to CLA. Okay. When Z is Z inverse belongs to CLA, that means Z must be belongs to Z. Okay. This will imply Z must be belongs to the group G. If Z is belongs to, since G by CA, it is the, if Z is belongs to G, then Z into CA, ZCA, this coset will also belongs to this. Since Z belongs to G, it will imply ZC of A belongs to G by CA. Okay, this factor group ZCA belongs to this factor group. If ZC belongs to this factor group, by definition of phi of XCA is equal to XAX inverse, that means phi of ZCA, okay, this will imply ZCA belongs to and phi of ZCA, the images of this ZCA, this is equal to 1. Phi of XCA is equal to XA X inverse, so ZCA will be equal to ZA Z inverse. That means what happened? For this element, for any element ZA Z inverse in the domain, codomain CLA, in the codomain CL, okay, there exists an element. The element is ZCA. Okay, there exists an element. The element is a coset ZCA, such that images of this ZCA is equal to ZA Z inverse. That means this element have a pre-image, that is this. It is arbitrary. For each element in the codomain, there is a image, there is a pre-image in the domain. So it is, hence it is onto, right? Hence onto, hence onto also. Since it is 1 and onto function, phi is a 1 onto function from this group only. Hence phi is a bijection. Now write, hence phi is a bijection. Write that. I will write here. Hence phi is a bijection from G by CA to CLA. Hence order of CLA is equal to order of G by CA. Is it visible? Okay, so make it here. Hence phi is a bijection from this to this, hence order of CL of A is equal to this. So here your proof is complete.